hydraulics and hydrology. I don't want to talk to donors. All right. We're rolling. So that's on the record. All right. So your project, which is really just a couple of problems related to storm sewer sizing with StormCAD, and then pond design, which is related to the example we did in class on Monday. That's due Friday before midnight. And then Friday of next week, we're going to have our final exam. It's going to be comprehensive. Let me put this on the board, or on here, just so that we're clear. Comprehensive. Equation sheets. 3. 3 with no conceptual information. What do I mean by that? No conceptual information. Anybody recall what I've said before about what's not allowed on the equation sheets?
Definitions.
No definitions of terms, right? Because there's a whole long list of terminology that I'm potentially going to draw from, ask you to define what those means, and I don't want you to have those listed on. It's supposed to be like an equation sheet, or you can have just an outline of problem-solving strategies. Like, for example, if you want to remind yourself how to do a certain thing step by step, you can put that on there. You shouldn't be explaining what's the difference between orographic lifting and convective lifting. That's not what the equation sheet is for.
3 front and back.
Yeah, 3 letter-sized also. Don't bring in, 3 letter-sized front and back with no conceptual information. And then we've got 120 minutes, but it's comprehensive with emphasis on more recent material. So that means that the things you haven't yet been examined on are going to be disproportionately more points available from those questions. So it's going to have some problem solving and some concept stuff. Computer related things. There's not going to be a WMS problem on the final exam because I gave you one on the second midterm, right? So you don't have to have WMS, but you should have Excel. So bring computer with Excel and StormCAD. Any questions? We'll talk more about it on Friday as well. All right, today we're going to talk about some structural measures to control floods. And we've seen some video of the flood wall with the gates up. Remember, I showed you that drone footage that I took a couple of years ago when Huntington was having some high water. In fact, the water's high again now. I was driving up to Athens over the weekend, and alongside, on Route 2, alongside the Ohio River, there were a couple of places where another foot and the road would have been underwater. So we're going to talk about different techniques that have been developed over the years to deal with the risk of flooding and how to avoid property damage. And then on Friday, what we'll do is we'll look at the economic analysis that allows you to know whether it's worthwhile to spend a certain amount of money to reduce the risk of flooding by a certain percentage. It's a pretty complicated probabilistic calculation that what you're doing on the one hand is weighing the known cost, and on the other hand, the projected savings in damage. So we'll continue flood control on Friday as well. So if you remember, we've talked about 2-year storms and 5-year storms, and there is a notion that infrastructure should be sized with an idea to how risky it would be if it failed. So for instance, someone may have a bridge across the creek to their house, and it may be that that bridge is flooded every year for a few minutes, but since there's only one person living on the other side of the bridge, and maybe they can park at their neighbor's house for the hour or two that the water's too high, maybe sizing a homeowner's bridge to a 1-year design standard is perfectly appropriate. But then if you talk about an entire neighborhood, and potentially some of the people in that neighborhood have health problems, or it could be a safety risk if people are isolated from being able to come and go too often. Maybe suddenly our threshold for hydraulic failure becomes a little bit higher, where we'd only want the water levels to rise and cut off a neighborhood maybe once every 10 years for a couple of hours. So an interstate highway is designed with a 100-year design standard, where they design the drainage so that, in theory, anything less than a 100-year storm isn't going to cause standing water in the roadway lanes. So that as you're driving along, a 50-year storm, you should be able to have safe passage on an interstate highway without the risk of having to drive through a puddle and lose control of your vehicle and all that. But then major structures, which are talking about like dams or levees, that there could just be millions or even billions of dollars of property damage or lives lost if that fails, then we go beyond thinking about 2, 5, 10, 15, even a 100-year storm, and there's something known as the estimated limiting value. So it looks at like the physical limits of how much rainfall could potentially come out of the sky for a watershed in a given amount of time. So if you had a really long duration storm, and if the soil was completely saturated before that storm occurred, and it was, you know, moisture precipitation from ground level up to 20,000 feet, I mean, they just take it to absurd lengths to really ask themselves, what is the biggest possible storm that could occur? And that's the idea behind the estimated limiting value, is an analysis that certain infrastructure is so important, like dams with loss of life or dams that could cause significant property damage, that instead of looking at a return period in years, they'll kind of flip the analysis to the estimated limited value and do it as a percentage of that, and size it so that they could accommodate those maximum flows without the structure failing. And an interesting thing to keep in mind when we talk about sizing infrastructure for a certain return period, like for example, if you have a 10-year design life, which means that you're sizing infrastructure to accommodate the 10-year storm, you're not just experiencing the 10-year storm in isolation. There are storms smaller than that that could occur, but also there's a chance, less than 100% chance, but there's a probability that larger storms could occur as well during the 10-year design life, and the probability is cumulative. We'll talk more about the probability part of it in class on Friday, but this figure is in our text to kind of illustrate, for example, if you have a 10-year design life, which is down here on the bottom axis, if you go up and you intersect with the 5-year return period, then it tells you the risk of a storm of having at least one event that exceeds the design limit during that design life. And so if you've got a design life of 10 years, and we're talking about how likely is it that there will be a 5-year storm during a 10-year period. And so what this is showing is that there's a 90% chance that you'd have a 5-year storm in that 10-year design life. So it's not a 50% risk, which is what you'd maybe be tempted to think, because it's the 5-year storm, there's the risk of that occurring, but also you could have a smaller probability of the 10-year storm happening, and the 20-year storm, and the 50-year storm. So there's, in the 10-year design life, if we're talking about what's the probability of a 5-year storm or larger, it's that or larger that kind of piles up behind the risk of the 5-year storm. So altogether, all of the cumulative risk of the 5-year storm and storms of greater intensity, you can see how to read this figure, 90% chance of a 5-year storm or greater in a 10-year period. So for example, just to take another instance, if we've got a 20-year design life, so that means we just want to consider in a 20-year period what storm size has only a 5% risk of occurring. So if we go up to the 5% risk size, there's only a 5% risk of a 500-year storm. But I mean, that sounds like a lot. Like if you had a loaded gun in your hand and you pull the trigger and there's a 5% chance it's actually going to shoot a bullet, you'd still be pretty careful with that gun. You wouldn't be pointing it towards people. So think about if you have a 20-year design life, there's a 5% chance that during that 20-year period you could experience the 500-year storm. So that maybe if you ask yourself what would be the outcome of the 500-year storm, would everybody in the town die? If the 500-year storm is going to cause a complete destruction of your dam, and the result of that dam's destruction is flooding and loss of life, then clearly that would be unacceptable. A 5% risk that everybody in town dies in a 20-year period, people would completely re-engineer the dam so that that wasn't the outcome of the storm. So cumulative probability is something we'll talk more about on Friday, and it's really important. And it kind of explains why we're willing to incur so much expense to avoid the outcome of flooding when we look at structural measures like levees and flood walls and diversions. So there's different ways for us to look at rainfall data, and you saw something, a reflection of this in the precipitation data frequency server. You can, if you have the real-time precipitation data, if you looked at the top 20 storms over a period, this is what it looks like if it is the top 20 storms. And some of those storms could occur in the same year. That's known as the annual exceedance series. If you allow it so that it's just the top 20 storms in a 20-year period, but the annual maxima way of looking at it is it's the top one storm in each year. And so by default, precipitation data frequency server will give you an IDF table that's constructed from this annual exceedance basis, which is more realistic, because if we really want to know the risk in any one given year of a certain size storm, we don't care if it's two storms in the same year and then a period that there aren't any storms in that top 20 ranking. But the annual maxima is how things were done in a lot of cases when it wasn't convenient to have automatic digital recording of flood data. Like sometimes back in the 30s and 40s and 50s, before they had electronic depth readings at streams, they would sometimes just have a gauge, and this would most likely be at really remote locations, sometimes up in the mountains. They'd have a stream gauge that they'd have to hike in and go and read the gauge. And sometimes they'd read the gauge every month to see what was the high water mark during that 1 month period. Sometimes they'd maybe only get to it once a year. And so they'd go in, they'd see, how high did the float get pushed up on a rod, and then it would stay at the high water mark. And so the annual maxima kind of just is a reflection of the way that data used to be recorded, where they wouldn't know in a case like back-to-back storms that are relatively large, like you can see these two, both pretty large storms, but you'd only have visibility to the larger of the two if you were seeing the annual maxima size of things. So there's a lot of different types of natural disasters that we have to be aware of. I used to tell people that we didn't really have tornadoes in West Virginia, but I've reevaluated my policy on that. We have small ones, right? It's not like Kansas or Oklahoma or something, but people out in the western part of the United States, in California, they've got a lot to worry about there. They've got wildfires and earthquakes, potentially tsunamis. That's just the natural disasters. There's also all the human-made disasters in California as well. But flooding is something that people in coastal areas have to be concerned with, people in wet regions like us. And I just saw some headlines today that, out in my old stomping grounds of the UAE, they had a huge storm there. Ordinarily in a year, they have 4 inches of rain in the UAE. And in a 24-hour period yesterday in the town of Al Ain, which is close to Abu Dhabi, they had 10 inches in one day. And this is a place that normally gets 4 inches a year. So that's 2.5 years worth of rain. in a 24-hour period. I can't imagine what it's like in Alain today. But nowadays we have pretty good warning when a storm is headed our way. Like it seems that it's not really a surprise. The tornado was kind of a surprise. My phone started buzzing probably 10 minutes before it got really windy. Hurricanes we know days and sometimes weeks in advance, but back in 1900 they didn't know because they didn't have satellites. They didn't have widespread wireless communication back in 1900. So there was a tropical storm that went over Cuba, through the Gulf of Mexico, and made landfall in Texas that was estimated to have winds of 145 miles an hour, killed 8,000 people in Galveston mostly. And it's kind of interesting to me because like my family lived in Galveston at the time, and they just kind of like got up and walked to California, like some of my relatives on one side left because of this hurricane and tons of storm damage that occurred. So the reaction in Galveston was to put in a barrier, like a seawall, to try and hold back the storm surge. You can see, I think it was in 1905 that they had it completed. And I don't know if it's still there, but this was just an example where when you've got 8,000 people who've died, suddenly people become willing to spend money to prevent it from happening again. And so, you know, this is at a time when the country wasn't as rich, when construction was a lot more difficult than it is now. Like the type of machinery that we kind of take for granted that can move earth and lay concrete really easily, it was more expensive and harder to do then. So it would be a huge investment to put in a seawall to try and hold back the storm surge. Another instance when I have this in my mind was back in the early 80s. I lived in Utah at the time, and they had a really wet winter with lots of snow in the mountains, and then suddenly it got warm and it rained in the mountains at the same time. So there was so much water coming through the canyons that they had to redirect what's called City Creek. It's normally not running in the middle of downtown. You can see what they've done is they've put sandbags up and they re-diverted what's usually just a small creek through the main streets of Salt Lake City. So they, you know, like called ordinary people out to help sandbag the side of the roads, and you know, people just came and gawked at it, a river, what's normally a very busy street. And that was, I think, the spring of 1983. And it caused quite a lot of flooding down in southern Utah as well. Just about ruined the Glen Canyon Dam because they were discharging water at the Lake Powell, is a man-made reservoir in southern Utah, and they were having to discharge water so quickly through the dam that it was causing cavitation and scour and erosion. So it was a really kind of sticky situation that they barely got through without the complete destruction of the dam back in the early 80s. Of course, we know that flooding causes damage here in West Virginia, and there are a lot of projects, locks and dams that have been put into place not only to make waterways navigable, but also to reduce the probability of flooding and try and decrease the damage that will occur when we've got wet weather. So this is a pretty nice looking house, completely underwater. And sometimes flood managers have to make the decision of like, where is the flooding going to be? Like, they have to, you know, if there's too much water, they'll have to bring up the level of the pool in the Ohio River at a certain location, and they kind of are in control of what locations flood. And hopefully when they do, it's agricultural areas, not built up areas that have homes, and it's still disruptive, obviously, to the farmer and to the people who depend on the crops. But generally, if you've got low-lying areas that have crops on them, then that's going to be kind of a no-brainer compared to flooding neighborhoods and homes. So it's not just the the direct damage that we have to consider as the benefits when flooding is avoided. It's not just you know, the drywall that has to be replaced and the carpet and the vehicles themselves, but when an area is at risk of flooding, people are less likely to build on it and businesses are less likely to come in and invest in a community. And so when you put flood protection in place, you're actually delivering a lot more value than the avoidance of the direct damage. There's also things that are known as indirect effects of flooding. And so you can put a dollar value on the avoidance of the cleanup costs, the health effects that can arise when people are exposed to the stress and the strenuous recovery process. So all of that's taken into account when we try and justify things like flood walls as the direct and the indirect damage that's been avoided. So floods obviously are going to occur in low-lying areas and in coastal areas due to storm surge, but sometimes they also happen in mountainous areas at the mouth of a canyon on an alluvial fan. I've got a diagram in a minute that shows you what an alluvial fan is. It's just basically in a mountain area where there's fast-moving streams that carry bedload like rocks out of the canyon. Then the rocks are deposited on the valley floor at the mouth of the canyon, and sometimes those are locations that people will build on, but then they're subject to flooding when there's a lot of rainfall in the watershed that contributes to flow in the canyon. There can also be flood related to when there are geotechnical failures and the ground level gets lowered, and also sometimes in areas that are influenced by structural measures. And this phrase here, structural measures, it doesn't mean structures in the same way that you understand that from taking a structures class. In flood prevention, structural measures means if you've put in something to reduce the risk of flooding, like a flood wall or a levee or a dam, those are all structural measures. And then non-structural measures are like rules preventing people from building in the floodplain. So structural measures are just engineered solutions that limit flood damage. There's some terminology that's important to understand. The floodplain are flat areas adjacent to a river. And so you can see right now where the land that we're on is a floodplain. And that's why it's flat in Huntington, where we're surrounded on all sides by hills, is that over the tens of thousands of years that the Ohio River has been meandering through this area, it kind of scoured flat the land that we're standing on. So we're on the floodplain. Next to the floodplain are going to be, well, there's, I guess, a slide in a moment. I'll show you where it differentiates between floodway and floodplain. But, you know, the main channel is where water would be most of the time, but the more water that's going through a river, then the profile of the waterway is going to get progressively wider. And so without a flood wall in place, then we'd have to identify what's the limit of the 100-year flood. And the boundaries of that go into maps that FEMA makes available on their website. It's called a FIRM, a flood information map. And the FIRM dictates how much you'd pay for flood insurance, and the cost of flood insurance can be like 5 times greater if you're inside the limits of the 100-year flood compared to if you're outside of the limits of the 100-year flood. So here's a picture of an alluvial fan, and this diagram just kind of illustrates that if you have a mountainous area and a stream that's coming out of relatively steep mountains, then when the valley floor occurs and like the slope of the channel decreases and the velocity of the water is slower, then suddenly all of those rocks and the sediment that was being carried downstream by high velocities settles out and is deposited on the valley floor. And so when people build on that alluvial fan, which can extend quite a long distance. This is a relatively small one, but the alluvial fan can be really long in some valleys. Then those are areas that are typically thought of as having an elevated risk of flooding as well. Okay, so here's this figure that differentiates between the main channel, which is where you'd expect water to be most of the time, the 100-year floodway, the 100-year flood plain. So if you have the water levels forced up by no more than 1 foot, you can build in certain parts of the floodway fringe. And this is something that people sometimes will do in West Virginia to extend their yards. There's a guy on the road that I live on where he always has people dump, like if they're doing a construction project, he has people dump their rocks and leftover bricks or soil next to his house, and then he pushes it into the creek so he can get more of the yard. But the problem is that if you have too much of the natural floodplain filled in, then what it's going to do, if you reduce the flood area, you can see the shaded region here, by reducing the area that water can flow, it pushes the water level higher. So there's a limit to how much of the floodplain you're allowed to fill in. And they define that limit as however much would cause no more than 1 foot increase in the flow depth compared to where it would be if the fringe wasn't filled in. So for the 100-year flow, they basically calculate what would be the water surface elevation for the 100-year flow, and then they say 1 additional foot is allowed by development in the floodway fringe. So I don't think the guy on the street that I live on, I don't think he's doing that calculation. I think he's just wants a bigger yard and nobody tells him not to put extra soil. But basically, by doing that, what people are doing is they're forcing the water level higher and kind of contributing to the risk of flooding. And that's called encroachment. When you reduce the capacity of the stream by adding soil in the floodplain, that's encroachment. And so the floodway is the area that has to be kept clear. No development is allowed in the floodway. That's the area that has to be clear to keep the rise in water surface elevation at 1 foot or less. But the fringe is where development can occur as long as the water surface elevation doesn't increase by more than a foot. The basic principles of floodplain management is what they're trying to do is reduce the susceptibility of structures to flooding, and that means using like waterproof materials or maybe raising the structure so that even if flood occurs, the habitable levels of the structure aren't underwater. Modifying the flood is more expensive than reducing susceptibility to flood damage, but modifying the flood means like diverting excess water around developed areas, which is a diversion, or by putting in a flood wall or building a levee. Those are efforts that are taken to modify the relationship between water surface elevation and damage. And then priority number 3 gets the most press. Like if you watch the news, that is, the National Guard coming in to hand out water bottles, or people shoveling mud out of basements, or volunteers showing up with clothes, helping people once they've had floods. It's important work to do, but it doesn't prevent the flood from occurring in the future. And so it's kind of like too little too late. But unfortunately, that's what gets most of the attention and most of the funding, honestly, is flood recovery rather than flood prevention. So it's kind of one of the ways that our political system isn't very efficient sometimes, when avoiding floods is invisible. Like if you spend $10 million on a diversion and a city doesn't experience flood damage, there's nothing to show on the news because the incident didn't occur. And so it becomes like the benefit is invisible and it's kind of abstract. Most people can't understand a reduction in risk probability. It's too abstract, whereas it makes people feel good to help out when someone's in need. And that's, an obvious kind of human instinct and emotion that doesn't connect with people as well as reducing flood susceptibility, which just feels like to most people big government interfering with what they want to do. People don't want to be told that they have to build their house on stilts, or they don't want to be told that they aren't going to be able to get a loan in a certain area because it's at risk of flooding. So they see it as like big government interference or a waste of money because the big event never occurred. I think you understand. The National Flood Insurance Program is a way of subsidizing flood insurance and making it cheaper in areas that are less risky and trying to encourage good behavior, encourage people to reduce the susceptibility of flooding and discourage people from building in risky areas. That flood insurance program requires that counties which want to have federally subsidized flood insurance have to have floodplain managers who try and keep the 100-year floodplain clear and managed. So they have to limit development in the floodway fringe to the 1-foot water surface elevation increase that I've already talked about. The flood insurance program is supposed to encourage people towards the use of flood-resistant materials, which will be less expensive to replace if the water levels do rise, and has to guide zoning and development to try and minimize damage in low-lying risky areas, and there has to be some sort of a system in place to prohibit the encroachment. All right. You're going to have some questions on the final exam related to 3 figures I'm about to show you. And if all you do to prepare for the exam is listen to what I'm about to say, you probably won't get to where you need to be. So what you need to do instead is you need to listen to what I'm going to say and also read the book description of this stuff, and then maybe think about it, and then come back to this video and listen to it again. It's kind of abstract, and most people aren't going to get it the first time. And so I'm just giving you the warning that I've noticed it doesn't seem to sink in for a lot of people. And I think it's not because it can't sink in. It's not that you're not smart enough, you can never get this, because it's not that complicated, but it takes more than one exposure. All right, so these 3 figures, first of all, this first figure is showing for a certain return period what flow rate is there going to be. So you develop a curve like this coming out of WMS, right? WMS would tell you 10-year storm, what is the flow rate Q? So the horizontal axis is like return period or exceedance frequency. So 2-year storm, 5-year storm, 10-year storm, 100-year storm. That's what would be on the horizontal axis. Vertical axis is Q, cubic feet per second, cubic meters per second. So this is just showing it as a line. Maybe it's curved, but there's just some sort of representation that would tell you the relationship between return period and flow rate. The next figure you'd get from a hydraulic analysis. So you'd get it from HECRAS, or you'd get it by applying the direct step method or the standard step method. It tells you, or just Manning's equation, really. Manning's equation, you can put in the flow rate and it tells you the depth, right? Manning's equation, Q equals A to the 5/3, slope to the 1/2, N times wetted perimeter to 2/3. So if you get the flow rate from WMS, from your hydrologic analysis, if Q is known, and you know a channel's roughness, and you know the slope of the channel, and you know, like, for example, the width of the channel, but then if the depth is not known, Manning's equation would tell you for steady uniform flow what's going to be the depth. We need to have some sort of a figure that tells us the depth as a function of discharge. So now discharge here, now it's on the horizontal axis, is the same thing that we got on the vertical axis from the hydrologic analysis. So just think, what we did was we took WMS and we said, tell me the flow rate for the 2-year storm, the 5-year storm, the 10, 25, 50, 100. And you connected the dots. So you can now know for a 40-year storm, what's the flow rate you're going to see. And then from Manning's equation or from HECRAS, you've got some sort of a model that relates flow rate to water depth. So stage is just talking about how deep is the water in the river. So the units there would be units of length. So feet or meters, it's how deep is the water. And the last relationship is for a certain depth, so stage is now on the horizontal axis, how much damage is going to occur. How would you get that? Well, what you'd do is you'd have a flood map, And so you'd know for a certain stage how much of the town is underwater. So you'd maybe use an elevation contour map. So if the water is 1,000 CFS, maybe the water isn't outside of the banks yet, so you wouldn't have any damage for certain stage. So you see how this stage doesn't start at the origin? This curve doesn't start at the origin? There's a certain amount of water depth at which no damage has occurred yet. But then there's a threshold beyond which additional water depth is now causing damage. And so sometimes this curve is steep, sometimes it flattens out. Like if the whole town is under 8 feet of water, there's maybe $20 million worth of damage. But now if the whole town is under 9 feet of water, there's not much more damage. I mean, it's just like a little more drywall that's become wet. Like all the carpets have been destroyed, all the appliances have been destroyed. So like what you could do is do some sort of analysis of at what elevation is a certain amount of property value. You know, it could be different buildings start to come underwater at different elevations, and within the building, certain cost components like carpets, electrical outlets are at a certain elevation. You get to another elevation, now you've lost all the light switches and electronic components, people's appliances and furnishings. So you could do some sort of an economic analysis that relates depth of water and damage. And so these three things together are going to be the lens through which we understand different structural measures. Different things like a levee is trying to reduce the damage that you experience it. And so what we have to figure out is how is a levee or a diversion or waterproofing, how do those different types of flood prevention measures actually achieve a reduction in damage? So that's why you need to know these different figures and what they mean, is because different types of flood prevention techniques, they avoid damage in different ways. So this just kind of explains that structural measures are things like reservoirs, diversions, levees, dikes, channel modifications. That's like engineered solutions, whereas non-structural measures could be like policies on where people can build or what kinds of materials they ought to use, or flood insurance programs that discourage people from developing in certain areas. So non-structural measures aren't like engineered solutions. So what flood control planning does is it considers like what is the relative appetite that people might have for imposing non-structural measures, and then what is the relationship between the cost of constructing certain structural measures and how much flood risk value they avoid. Honestly, I don't remember what's the deal with Tigert Lake. Let's take a look at this. Yeah, I think this is just an illustration of a structural measure and how much it costs and what sort of precipitation it can accommodate. So Tigert Lake, it can store 4.56 inches of precipitation within the drainage area. And so the way some of these things are described is that in 1985, that lake existing prevented $195 million of damage just for that year alone, because they estimated if that lake wasn't there to absorb the incoming flow, it would have continued downstream and caused a $200 million worth of damage. So it was completed in 1938 and has prevented $1.2 billion worth of damage, and it was originally constructed for $18.5 million. So I think this is just an illustration of like when you've got a successful structural measure, years and years after it's been constructed, you may be able to retrospectively look back and tally up the costs and the benefits. And you know, it's pretty good return on investment, But back in 1938, when it was being built, they didn't know that there would be a storm in 1985. And they didn't know that there would be so much development and value that in that storm alone, $200 million worth of damage would have occurred if the lake hadn't been constructed. So, like, it's a big investment, especially, you know, nearly $20 million back in 1938, the heart of the Great Depression. That probably was a lot of money and a real sacrifice. There's other things that money could have been spent on, but it was a success. So, flood control reservoirs. This is showing what they do change and what they don't change if you've got a reservoir like Tigert Lake. It's not changing the relationship between the stage and damage. So like having a reservoir between the town and the watershed. Let me just sketch this out on the whiteboard here. So we've got a reservoir, or I'm sorry, a watershed. So it's a dendritic watershed. You know, we've got all these side streams and so on. And so what we did was we put a lake here, reservoir. And water comes out of the reservoir, and here's the town. Okay, so if the reservoir wasn't there, the lake would just, or the water would just be going straight past the town, and the reservoir's kind of acting like a shock absorber. I mean, you've done pond calculations, right? This is a pond on a grand scale, and the purpose is to flatten the peak so that you've got less flow coming through the stream quite so quickly. So it's not changing the relationship between stage and damage. Like, just because we put a reservoir up here, if the water level gets up to a certain elevation, it's still going to cause the same amount of damage before the reservoir was there. So there's no change to stage versus damage, and there's no change to stage versus discharge either. That's just affected by, like, the shape of the channel, the roughness of the channel. So we get this from the hydraulic analysis. And having a reservoir upstream doesn't change that. What it does change is for the certain exceedant frequency, what discharge will be coming through the stream. So like, what kind of Q are you going to see after there's a 10-year storm? So after there's a 10-year storm in the watershed, that flow gets absorbed by the reservoir. And so the Q isn't as high as it would have been during a 10-year storm because the reservoir kind of acts as that shock absorber. So ordinarily, the flow rate would be higher, and this is showing the dashed line is the modified curve of exceedant frequency versus discharge. So it's below, and so you have less discharge for a certain return period, and because there's less discharge, the water levels are lower, and because the water levels are lower, you're going to have less damage. So that's kind of like the sequence of changes in these three relationships for a flood control reservoir. I don't remember what this video, oh, that's just Tigert Lake again. Okay. One of the things that we have to be aware of, though, is that reservoirs can act as a sediment trap over the long term. If water's coming out of a watershed and then suddenly slows down in a reservoir, all of the suspended solids can sink to the bottom. All of the sand and gravel that's coming out of the watershed could fill up in the reservoir. So you could, over time, lose capacity in your reservoir. And if you lose capacity over time, then you lose protection. And then the other thing is that when you've got protection like this, people may feel a sense of complacency in the town. And so then they start developing even more than they did before the reservoir was put in place. And so what if suddenly this damage versus stage relationship changed, where with a certain water surface elevation you had even more damage because there's more development? And so sometimes whenever you provide protection for people, they will be more reckless. And I had a professor when I was working on my PhD who was a transportation engineering faculty member at Purdue. And he kind of made a name for himself by going through a lot of like survey data and highway safety data and kind of conclusively proving that things like seat belts and airbags just lead to people driving more recklessly. Like they have more of a sense of security, so they drive faster with less attention to what they're doing, and that those protections get largely canceled out by people being more reckless. And so we have to be really careful about structural measures that, we can provide all this extra protection, but then that shouldn't have people let their guard down with, for example, allowing development on the floodway fringe or shying away from flood-proof materials. A reservoir is suitable if you are trying to protect area that's really spread out. What you're doing is you're concentrating the water into one location, and it's going to be expensive to build a reservoir because dams are costly to construct. A lot of engineering certainty is needed for a dam because the failure could be so catastrophic. So they're not cheap, but it's suitable when the area that you want to protect is really spread out. If an area is concentrated and you don't have to protect like a wide area, then it's much easier to just put a ring around the town that you're trying to protect. And so reservoirs are more suitable if it's dispersed area that you're trying to protect. It's obviously only suitable if you've got land available to build the reservoir, and then they'll always do an economic analysis to make sure that the value of the property that's being protected is justified when compared to the cost of construction. Diversions are similar in outcome, which is providing protection to the town, but in a diversion, instead of having that shock-absorbing reservoir, what you might do instead is have like a secondary bypass. This is looking down from above, right? We're looking from above. And so if you had, this is the main channel, and this is like an auxiliary channel where water only flows through that bypass when the water level gets really high. A diversion would provide protection by rerouting flow away from a center where damage could occur. So the way that it does that is not by changing the stage versus damage relationship. It doesn't change the stage versus discharge. It changes the exceedant frequency versus discharge, because there's suddenly going to be certain storms that are not contributing to flow in the main channel, but they're contributing to flow only in the auxiliary channel. So this curve shows where that change in increasing exceedant frequency does not increase the discharge through the main channel. All right, we're out of time. It's 1:49. I'll let you go a minute early so you can go get ready for your senior design presentations, but we'll pick up this discussion on Friday.